Hello everyone, my name is Thomas Ostersen. I'm a PhD student at the University of Tasmania, and today I'll be talking about some of the research I conducted as part of my PhD project investigating the geoelectric structure of the Tasmanian lithosphere using magnetotelluric or MT methods. I'll start the talk off with a quick overview of Tasmania's geological setting, as well as one slide overview of the MT method. I'll then discuss the datasets we acquired in 2016, as well as some of the legacy data in Tasmania that I was able to incorporate into the research project. I'll then jump straight into an interpretation of the 3D models that I generated from the regional AusLAMP scale, the AusLAMP dataset. This will be followed by an interpretation of 2D transect models from Western Tasmania across key geologic terrains. I'll finish off the talk with a presentation of a potential use case for these regional scale AusLAMP models, presenting a model where I used it as a starting point for higher resolution 3D inversion. So Tasmania has a long and complex tectonic history. It's often the subject of scholarly debate. I'm just going to cover the absolute basics, however. So we often divide Tasmania into two basement terrains. The East Tasmania terrain, which is the youngest. It contains, the oldest rocks in this terrain are from the Ordovician, just a thick package of folded turbidites called the Mathina supergroup. To the west of this, we have the West Tasmania terrain, which itself is divided into a series of tectonic elements, the oldest of which is the Rocky Cape element. This contains a package of Mesoproterozoic deformed quartzites with a distinct Laurentian provenance. The Tainan element is a Meso to Neoproterozoic package of deformed quartzites, and wedged in between the two is the Dundas element. All three elements, and the West Tasmania terrain in general, records a Cambrian arc continent collision that profoundly affected the nature of this terrain. It was responsible for emplacement of a series of mafic ultramafic complexes, largely in the Dundas element. And the Dundas element also contains a belt of Cambrian arc volcanics that are highly prospective and host a number of world-class polymetallic VHMS deposits. The two terrains, east and west, were amalgamated in the Devonian as part of the Tabarabaran orogeny. This reactivated a number of the structures from the earlier Cambrian orogenesis, and also coincided with voluminous granitic intrusion. Some of these granites are highly prospective for tin tungsten mineralization as well. After the Carboniferous, we saw a return to sedimentation with the deposition of Permo-Triassic sediments of the Parmena supergroup. These were extensively intruded by dolerite in the Jurassic as part of the Karoo-Farrar large igneous province, with other outcropping examples observed in South Africa and parts of Antarctica. This was a large-scale tectonothermal event that immediately preceded the breakup of Gondwanaland. And much more recent, we have the eruption and placement of Cenozoic basalts. So taken together, this post-Carboniferous cover really complicates interpretation of the basement. And in order to do that, you need a method, a geophysical method, that can peer through this cover. And this is where MT comes in. So MT, magnetotellurics, it's a passive geophysical technique in which we measure the Earth's electric and magnetic field at a point on the Earth's surface. The relationship between these fields contains information about the Earth's bulk resistivity beneath the instrument, and bulk resistivity in Earth materials is influenced by several factors, including temperature, porosity, the presence or absence of certain mineral phases, and once you get deep enough, proton diffusion. So since a number of these factors are depth dependent or dependent on the geochemical state of the rocks, putting all that together, geoelectric models contain a wealth of geological information that can really help to inform tectonic interpretations. So this is the data we have available to us. In 2016, as part of the Tasmanian leg of the AusLAMP project, that's the Australian Lithospheric Architecture Magnetotelluric project. I'm sure we'll hear more about this in later sessions. We acquired 57 long period sites across the island at a site spacing of about 35 kilometres. We also acquired 2 higher resolution broadband transects for shallower imaging, and some of the legacy data available includes a large array of broadband sites acquired by Moombarrigga Geoscience between 2008 and 2010 for KUTH Energy as part of a geothermal exploration campaign. So I'll be talking about all these data sets with the exception of the northern transects, which unfortunately suffered from a significant degree of power line noise. Jumping into the interpretation and modeling of the AusLAMP dataset, the end goal here was to generate a 3D model, and to do this we used an inversion algorithm, ModEM, of Anya and others. And since the data is sensitive to a depth range of about 5 to 100 kilometers, it's important to have a large starting model with a significant amount of padding to avoid boundary conditions in the model space. And a big consideration for this Tasmanian dataset is the fact that we're on an island. It's surrounded by conductive seawater, and we also have thick offshore sedimentary basins, containing unconsolidated sediments that are likely to be quite porous and quite conductive. So in order to account for these, I built into the modelling space, obviously seawater at 0.3 ohm meters, but also included 10 ohm meter conductive sediments from the AusSeaBase dataset. And here's the final model, or the preferred model. So this is the AusLAMP model. I've stripped the padding cells from the edges of it, and I've sliced the model to a depth of 8.7 kilometers. These little red dots, they represent the AusLAMP sites used in the inversion, and these pinky red structures, they're isosurfaces containing regions of the upper crustal model space with resistivities less than 6 ohm meters. So the structure that immediately jumps out at you at this shallow depths is this arcuate region of elevated conductivity between the Tamar River Valley up here and pretty much Hobart in the south. This is the Tamar conductivity anomaly. It's a known structure. It was first identified in the 1970s. It was later studied in the late 80s, early 90s. But this is the first time we've seen it at this high resolution and in this detail. You can see the Tamar conductivity anomaly. It manifests in other data sets, such as this shear wave velocity model from Simone Piglia. You can see it here as this arcuate region of low shear wave velocity. And the preferred interpretation for the Tamar conductivity anomaly, at least at upper crustal depths, is that it's just a highly fractured, highly sheared zone separating the East Tasmania and West Tasmania terrain. So elevated conductivity is likely due to fracture-induced porosity. Moving to the west now, I've overlain a 3D geology volume from the statewide 3D geology model, and we see a reasonably good correlation between graphite-bearing rocks of the Arthur lineament and a region of elevated conductivity. So graphite is a great conductor, so this relationship seems to be causal. Elsewhere in the model space, we see a reasonable correlation between areas of elevated conductivity and inferred ultramafics, Cambrian ultramafics at depth. These ultramafics are invariably serpentinized, and the process of serpentinization has been observed to increase conductivity by about an order of magnitude. But the relationship between ultramafics and elevated upper crustal conductivity is a bit complicated, given that a lot of these ultramafic slivers are fault bounded, so elevated conductivity might be due to a mixture of both serpentinization and fracture-induced porosity. Looking at the more resistive parts of the model space now, we see a good correlation between highly resistive parts of the upper crust with regions of Tasmania where you've got Devonian or Cambrian granites inferred, mostly from gravity observations. Granites are crystalline rocks with low porosity, so this seems to make sense. Moving on to mid-crustal depths in the model space now. We tend to see an increase in conductivity and intensification of conductive anomalies at these depths. And in West Tasmania, it's interesting to note that the peak conductivities tend to occur beneath the surface expression of Cambrian amphibolite to eclogite facies metamorphic complexes, highlighted here in red. These complexes are believed to be the remnants of partially subductive passive margin material that was rapidly exhumed following the cessation of collision in the Cambrian in the Tainan orogeny. The preferred conduction mechanism for these mid-crustal conductors is graphite, basically, along grain boundaries, potentially exolved from CO2-rich fluids emanating from partially subducted material at the edges of these Proterozoic blocks. Moving on to the lower crust and lithospheric mantle now. We see the intense values, both high and low, the extremes of resistivity that we observed in the mid-crust reduce in intensity by about an order of magnitude. We see the Tamar conductivity migrate westward, Tamar conductivity anomaly that is, and we also see a change in conductive mechanisms at these depths. Graphite, carbon becomes less important as a conductive mechanism, given decreasing stability at higher temperatures. And we begin to see hydrogen content in anhydrous minerals play a key role. Into the mantle now at 41.6 kilometers. The key conductive mechanism at this depth is essentially hydrogen content in pyroxene and olivine. Now, hydrogen behaves as an incompatible element at these depths, so you can think of conductivity imaging mantle fertility at these depths. And the interesting thing to note is that East Tasmania terrain is considerably more resistive than the rest of Tasmania. So this implies that the mantle beneath the East Tasmania terrain is different to the rest of Tasmania and is considerably less fertile. Relatively low resistivities in the central keel, in this north-south keel in the Tasmanian mantle, in the central Tasmanian mantle. That might be imaging some relict mantle fertility left over from the event that triggered the large igneous province, the Jurassic dolerite large igneous province. That's the preferred interpretation at this stage. Moving on to the Western Transect now. This is a much smaller data set. It's 34 MT sites in total, over 80 kilometres along the Lyell Highway, between Granville Harbour and about 30 kilometres east of Queenstown. The sites are separated by about 3 kilometres, but there are a number of gaps. This is just due to inaccessible terrain around some of the west coast rivers. As with AusLAMP, the end goal here was to create an inverse resistivity model, in this case a 2D model. I used the Occam 2D code from Constable and others to generate this. And it's important to note that the data sensitivity of the Western Transect, the depth sensitivity range is about 1 to 25 kilometers, although it varies across the Transect, but that's about it on average. Visualizing the model, I did all my interpretations in 3D using Geoscience Analyst. Here's the 2D Transect model stripped of padding cells and clipped to a maximum depth of 40 kilometers. And comparing it to the AusLAMP model now, we see a pretty good agreement between the two models, which is quite interesting given that they're two different data sets and the models are generated using different methods. So good agreement is a good outcome. Here's an oblique view looking north of the 2D transect. These little spheres are the data points. And I'm just going to overlay now copper, gold, silver deposits of the Lyell mineral field. So this is a world-class copper mineral field around Queenstown in Western Tasmania saw near continuous operation from the late 1800s to about 2015, in which 1.8 million tons of copper were extracted. And there is this, it's very subtle, but there seems to be some conductive structure linking that area to a mid-crustal conductor further to the west. If I overlay some major Cambrian fault structures that were reactivated in the Devonian now, the Great Lyell and the King River Fault, we see a reasonable correlation between these west-dipping faults and that subtle conductivity structure. And I think this relationship is causal. Overlaying the 2006 3D geology model now, here is the Tainan metasediments. Unfortunately, the models are clipped off at a depth of 10 kilometers. Yeah, and we see the key thing to note here is this region of elevated conductivity beneath the Tainan. I'm interpreting this as being a region of elevated conductivity due to graphite from that partially subducted material that we observed in the AusLAMP models. More resistive parts of the model space in the central parts of the model seem to correlate quite well with inferred Cambrian granites, with the exception of where the granite is pierced by that fault structure. And further to the west, we see quite a good correlation between shallow surface anomalous conductivities and the inferred location of serpentinized Cambrian ultramafics. Even further west, Devonian granites seem to account for some of the elevated resistivities in that part of the model space. So I think that's a pretty good story. The relationships observed in AusLAMP fit with the relationships in the Western Transect. I'll just pivot to the final part of the talk now, where I'll cover some of the modelling work I did on a legacy MT dataset acquired between 2008 and 2009 in eastern Tasmania as part of KUTH Energy's geothermal exploration campaign. This is the dataset. It was originally acquired as a series of transects, but then it was later infilled with more data, and it's the perfect candidate for 3D inversion. So I sought to generate a 3D model, just like I did with the AusLAMP dataset, using the same inversion code. But the key difference here is I used the regional geoelectric structure derived from the AusLAMP modeling as a starting point for higher resolution modeling of this KUTH dataset. Here's some depth slices through the final preferred KUTH model on the left, and equivalent depth slices through the AusLAMP model, which was the starting point. So one of the key takeaway here is that we can clearly see regions of the model space where the inversion algorithm has smoothed the blocky structure inherited from AusLAMP, and it gives us a good sense of where the data is sensitive to in the subsurface. I think that's a good result. It gives us geologically feasible structures, and I'll summarize these with this little video I recorded. So here's the final KUTH model stripped of padding. We're just slicing through from top to bottom. There's some semi-transparent pink isosurfaces that encapsulate regions that are really conductive with the resistivities less than 1 ohm meter. There's some semi-transparent fault structures interpreted from aeromagnetics and topography data. And finally, that coloured surface represents the granite roof topography in the area interpreted from gravity datasets. So yeah, it's a pretty good geological story. You've got peak conductivities occurring at the locations where Devonian granites are pierced by recently activated fault structures, all beneath insulating Permo-Triassic sedimentary cover. So to conclude the talk, this research project has added new 3D and 2D inverse models that for the first time characterize the whole of the Tasmanian lithosphere in terms of its electrical resistivity. We've also been able to demonstrate a potential use case for regional scale AusLAMP models as a starting point for high resolution modeling. I should also mention we have a paper currently in preparation that describes the interpretation of the regional scale AusLAMP model for Tasmania in greater detail. So watch this space. I also need to thank, I'd like to acknowledge people from Geoscience Australia, University of Adelaide, Geological Survey of South Australia, Mineral Resources Tasmania, the University of Tasmania, as well as Dr. John Bishop from Minor Geophysics. This project couldn't have happened without their generous help. And with that, I'd like to close the talk off, and I look forward to hearing your questions. Thank you.